Hey everybody, this is Professor Corey and Professor Victoria. We are the Professors DuBois, and this is part 5 of our buffer series. And we're getting into a little more complicated calculations in this part of the series where we're going to make buffers using a different method than the direct addition method. And we could actually call this an acid-base reaction to make a buffer. So if I look at this problem, I noticed right away I've got my weak acids, my hypochlorous acid, and you know me, I'm going to write the acid hydrolysis.
And this just helps us identify what this buffer system is, so we can identify what our conjugate base is to this weak acid. So we have, in order to have a buffer, we need some amount of our weak acid, our HClO, and we also need some amount of this conjugate base, the ClO minus.
Now, I could go to the stock room and look for a bottle of ClO minus, and I'm not going to find it. Now, but I might find a salt. I might find like a sodium hypochlorite. But what we're assuming in this scenario is that we just don't have any conjugate base, and we need to make this buffer. So this is where I'm going to show you something kind of interesting. Where this says how many moles of potassium hydroxide. KOH is a strong base, right? So I'm going to write this as a net ionic equation. I'm just going to jump right to it. So we're going to have the OH minus. That potassium is going to be a neutral ion. It's also going to be a spectator ion. And if I write, take my strong base, it's going to react with the acid, right? This is going to be a single arrow. And we are going to make, lo and behold, look what we're making. We are making conjugate base. So we can actually produce conjugate base by reacting strong base with this weak acid. So where we have to be careful, we need plenty of this strong acid. We need to have stuff left over.
Weak acid.
We're going to need some of that left over. And we're going to need to produce a fair amount of the conjugate base. And that's where this gets a little bit complicated. But we're going to walk you through exactly how to do this problem.
So we need a buffer with a pH of 7.3. So we can use our Henderson-Hasselbach equation to figure out what our ratio of our base to acid we need once this reaction is complete. So we have our desired pH of 7.30 and our Ka was provided, and our pKa then is the negative log of that, which is 7.42. So if we subtract our 7.42 from both these sides and take the inverse log, we will have our ratio of our base to acid, which ends up being 0.759. Now this is either in molarity or moles, and what we want you to think of is moles. So we have a ratio of our moles of base to our 1 mole of acid, and this helps because as we add solutions together, our volume changes and therefore our molarity would change, and it's a lot easier to just use moles when we're doing these calculations. So we go back to our reaction here, and this is the ratio we need to end up with, is this 0.759. But we are limited by how much we start with. It tells us that we have 150 milliliters of our 0.443 molar acid. So if we can convert our 150 milliliters to liters, and then we have our 0.443 molar solution, we get moles of our acid. And that's our initial amount, 0.06645.
So we're just carrying some extra digits here. We'll round our sig figs at the end. So that's how much acid we have in moles. So this is a mole table. And that's how much acid we have.
That's how much we're starting with.
0.6645. Now we're going to add some amount of base to produce our conjugate, but we don't really know how much. So we're just going to call that X.
And we're starting out with no conjugate base in this scenario. So our base will go down by some amount. Of course, we're going to also have our acid go down by that amount, and our base will go up. So after this reaction is complete, we will have 0.06645 minus that amount, and we will have that amount of base. And we need it to equal that ratio of 0.759 that we calculated before, because we need this buffer to be 7.3.
So at equilibrium here, my ratio of base to acid is X.
It's after the completion reaction, yep, so it's not an equilibrium. We're going to have base over acid is X over point.
And this is going to be equal.
Missed a zero there, 0.06645.
You are right. And I can fix that. And this is equal to the ratio we calculated.
And base over acid equals base over acid.
Okay, so what I'm going to do is I'm going to multiply both sides by 0.06645 minus x. So I'm going to have to distribute over here.
Yep.
So I'm going to end up with x equal to, that's this x, equal, so I'm multiplying both sides by this here. And when I distribute, I get, what do I get for values there? 0.0504. Now, I got that from 0.06645 times 0.759. And then I got to multiply negative x times the 0.759. That's going to be minus 0.759x. I can combine like terms. I'm going to add 0.759x to both sides. 759x. Now remember, x is 1x. So this ends up being 1.759x is equal to 0.0504. I'll divide both sides by 1.759. And x is equal to 0.0287.
Now this is moles. We are in a mole table, so this is moles of, well, it's the moles of hydroxide that we added. It's also the moles of weak base that is produced.
So what was the question even asking for? I think it's worth going back. We want to know how many moles of potassium hydroxide. We've got our answer right there. 0.0287 moles is the amount of potassium hydroxide that would have to be added to produce that buffer.
Yeah.
Do
we have one for them to try?
I believe we have another. And this is challenging, okay? There's a couple extra steps here, and I would encourage you to pause the video and give this a try on your own, and we'll do a quick run through it so you can check your result.
I think the only extra thing that you're going to need to do is once you solve for your moles of hydroxide, it gives you a molarity of that hydroxide, and you just have to convert that to the amount in volume in milliliters. So that's just one extra step. So follow the same thing that we just did, and then you have one extra step to go from moles to volume of your hydroxide.
All right, so should I start out with the Hasselbach equation or just start out with my reaction?
I would go with my, probably the Hasselbach. Let's get our moles.
Let's get our ratio
that we need. So we know what system it is. It's the hydrocyanic acid. So it's the HCN CN minus buffer system. And our Ka was 4 times 10 to the minus 10th. So our pKa is 9.40. So that's equals 9.40 plus the log of our base over acid. And we're going to solve for base over acid. And again, you're going to subtract your 9.4 from both sides. You'll get a negative. That's okay. Take your inverse log of that. And now you have your ratio, once all is said and done, is going to be 0.692 moles of base to 1 mole of acid. So our reaction that we're going to use to produce the conjugate base that we don't have any of is we have HCN is going to react with our OH minus to produce that CN minus. So as long as we don't use up our HCN and we can have our ratio at the end, we know how much we start with of our HCN. That's provided, so that's 0.35. We've got 0.393 molar HCN, and we have 250 milliliters. So start with your 250 milliliters, change that to liters, and then use your molarity. Again, we're solving for moles of acid that we're starting with.
And this is the HCN, so that's the 0.393
moles per liter. We like to change that capital M into moles over liters so we can cancel. And the moles that you start with are 0.09825. And carry a couple extra digits as we go through this so that we don't add any error. We'll round at the end to the correct number of sig figs. So we're going to represent this hydroxide with X. We don't know how much we have to add. We know we started out with 0 of our conjugate base, and that is going to go up by X. And at the completion of this reaction, we are going to just represent these by X, and this ratio has to equal the ratio that we're looking for. So base over acid. Base is X, acid is 0.09825 minus X, and that has to equal the ratio that we solved for using that Henderson-Hasselbach equation, which was the 0.692 over 1. This is probably the only time that we're going to use cross multiplication here, but
so we're gonna multiply both sides by the 0.09825 minus X. So we'll distribute that over here. And what we're gonna end up with is X, and that's this X right here, is equal to, so I go 0.692 times 0.09825, and I get 0.0679 minus 0.692x. I can combine like terms. Remember, X is 1X. I'm just going to scroll this a little bit. So I've got 1.692X equals 0.06799. So I'm going to divide both sides.
And X equals 0.0402. This is your moles of hydroxide. This is the moles of hydroxide that you had to add. Now, we also had that we had a 0.227 molar solution, and it's asking for how many milliliters. So we have moles with molarity. We can get to volume, no problem.
So we have 0.0402 mole OH minus. And we have a molarity?
0.227
now check
mole
this
per
out.
liter.
I have to put the liter on top. See that? So my 0.227 mole is actually in the denominator, so it cancels for 1 liter. And we're going to go to milliliters.
Yep, so we can do multiply by one more factor. Liters on the bottom.
Liters, 1,000 mils. So this is going to equal
177 milliliters. And if we go back up to our Ka, that only had 2 significant digits. So technically, to 2 significant digits, it would be 180 milliliters.
180 milliliters of my hydroxide ion, which is coming from the potassium hydroxide. So we had this solution made up, and if we added 180 milliliters of that solution to 250 mils of the
HCN
at 0.393 molar, we would produce a buffer with a pH of 9.240. Now, this is a pretty challenging question. You might have to work through this one a couple of times before you start to get comfortable with it. And I would recommend doing so. So, you can try to solve this problem, and then you can kind of put it away, and maybe half hour, an hour later, try it again. Keep working these problems until you can do them back and forth, upside down and backwards, and I'm very confident that you can master this material. So thanks for watching our buffer series. We plan to add to this series in the future, so stay tuned.
Bye-bye.